Hello. In today's session, we will discuss minimum critical current estimation. First, here's the agenda. We'll begin by discussing the isotropic and anisotropic critical current properties in superconductors, using MgB2 with isotropic critical current and YBCO with anisotropic critical current as examples. Then, we'll talk about the minimum critical current in superconductor magnets. In superconductors, critical current refers to the maximum current that can maintain superconductivity. For details on critical current, you can refer to Chapter 1.1.1. Some superconductors exhibit anisotropic properties depending on the external magnetic field. Isotropic superconductors include niobium titanium and MgB2, which are made in wire form. Anisotropic superconductors include REBCO, made in tape form. Let's start with MgB2, which has isotropic critical current. When measuring the critical current with varying angles of the external magnetic field, MgB2 exhibits isotropic properties, where the critical current depends only on the magnitude of the magnetic field. The picture at the bottom left shows the cross-section of an MgB2 wire, and the graph at the bottom right represents the critical current of MgB2. As mentioned, MgB2 demonstrates critical current dependent solely on the magnitude of the magnetic field. Next, let's discuss YBCO, which has anisotropic critical current. When measuring the critical current with varying angles of the external magnetic field, YBCO exhibits anisotropic properties, where the critical current depends not only on the magnitude but also on the angle of the magnetic field. The picture at the bottom left shows the cross-section of a YBCO tape, and the graph at the bottom right represents the critical current of YBCO. You can observe that the critical current varies with both the magnitude and the angle of the external magnetic field. In the middle illustration, you can see that the current flows along the A-axis, while the angle of the magnetic field changes along the BC plane. When the magnetic field approaches the B-axis, the maximum critical current value along the A-axis is observed, whereas when the magnetic field approaches the C-axis, the minimum critical current value along the A-axis is observed. Moving on to the minimum critical current in superconducting magnets. In superconducting magnets, the critical current is partially determined by the following factors: the angle of the magnetic field entering the wire, the change in magnetic field magnitude due to operating current. Taking a racetrack as an example, you can see in the illustration on the right that the critical current varies at each position. Knowing the minimum critical current is essential for determining the maximum operating current, which enhances the magnet's performance, cost-effectiveness, and reliability. Therefore, estimating the minimum critical current is crucial in magnet design. Based on the preceding content, determining the minimum critical current is necessary for magnet design. One method used to select the minimum critical current value is the load line method, which involves the following steps. Considering the anisotropic properties of the tape, the minimum critical current of the magnet with respect to the operating current is determined through finite element analysis. The intersection point of the graphs, representing the operating current, and the critical current determines the critical current. The operating current is determined based on the ratio to the critical current. The following example illustrates the quantitative values obtained using the load line method. The left graph represents the minimum critical current of the magnet for each operating current, obtained from the right FEM results graph. The intersection point of the two graphs determines the critical current as 96.4 ampere. Typically, The operating current is selected at around 70% of the critical current. Therefore, in this example, an operating current of 66.2 ampere was chosen for magnet design. In summary, anisotropic superconductors have different critical currents depending on the direction. The minimum critical current estimation is a method used to find the maximum operating current. The load line method in superconducting magnets helps determine the minimum critical current of the magnet, which then sets the maximum operating current. Maximizing the operating current is crucial for improving the magnet's performance, cost-effectiveness, and reliability. Typically, the operating current is set at around 70% of the critical current. Thus, I conclude the presentation on minimum critical estimation. Thank you for your attention.